to jest to możliwe, no ale mam...
Czuwamy nad...
Janek tu nie ma. Naturalnie. Some noises from Zoom application.
To co idzie do od pani tej Zooma?
Wiesz co to jest? To jest wentylator na tobie.
Być może, tylko to co...
cały czas.
Tylko coś, co... Teraz to ja się słyszę skądś. Skąd ja się słyszę? Któryś... Raz. Ja się skądś słyszę. Raz.
Możesz tu podejść?
Już. Ja?
Nie. Jakbyś jeszcze raz do tego mówił.
Nie. Meetings. To jest na stronę czasu.
Raz.
Pani się...
Nie włączył się tutaj gdzieś mikrofon?
Pan Marcelo jest na kolejnym spotkaniu.
Wiesz co? Daj teraz dźwięk z tego.
Skąd?
Scientist in the lab and working on processes and so on. I've been at the Becker Island for a year.
Fantastic.
Ale trzeba poinformować pana Marcelo, że zaczyna za godzinę. Ja muszę go nie mówić, niestety.
I heard somebody say my name in Polish, but
Yeah, I know, but they've been talking to each other for a while, and I was like, hello, somebody there? Can somebody hear me? Okay.
hello, can you hear us?
So from what I Bartek, he said that they could see me and that there was an issue with the noise, that they were trying to solve it. I don't know if it's my computer, because it has happened in the past, that when I log into meetings, people are like, oh, what's that noise? So actually I could look for a different set of headphones or something if that is the problem. But they're not responding in any way, so I'm like...
I'm being asked to kindly leave. Have to join later. All right, I'll see you guys. Best of luck on it again, everybody.
Okay, weird. I tell you something, they don't tell me anything. Did they chat with you? Oh, cool.
That's Monica.
A oni nie mogą uczestniczyć w panelu równolegle?
Nie, to jest kolejny panel.
Dobrze, po przerwie, ten sam, tylko po przerwie.
Tak. Tam już mamy...
Ale może wysłuchać.
Już nie ma pana Marcelo.
Dobrze.
Poinformowałem, że zaczynam za godzinę.
Dobrze.
Pan Marcelo już od 10 czekałem.
Bardzo miło z jego strony.
No, momencie, to co minutka, tak?
Much better.
Możemy zacząć?
Nie, minutkę, ja powiem. Minutę mamy, nawet nie całą.
Good afternoon, everybody. My name is Bartosz Zieliński. I'll be leading this panel on behalf of ML System. I'm the manager of Research and Technology Transfer Department for the ML System. This panel is dedicated to modern photovoltaic energy systems, and we are going to be tackling problems on the photovoltaic cell level, on the photovoltaic module level, and on the system level. For the first part of the panel, the participants and the speakers who will be joining us are Ali Said from Using Engineering, Monica Aleman from Becquerel Institute, and Bartłomiej Kras for Impact Clean Energy Technology. Welcome. Our first speaker is going to be Ali Said from Using Engineering. Ali is the Vice President and General Manager for Europe and the Middle Ages on behalf of Using Engineering. He has 13 years experience in semiconductor and photovoltaic manufacturing, which are followed up by 20 years experience in IT technology, in infrastructure development and software development and security. He's going to be sharing with us the insights on the tandem solar cell going beyond the heterojunction. So without further ado, Ali, please, the floor is yours.
Thank you very much. Hello, everybody, and I want to thank you very much for giving me this great opportunity to present to you some of the latest technologies we've been working with. Before I start, I would like to say that we use glass a lot, everywhere, every day. And even in our manufacturing facilities, we use glass. But I have never learned so much about glass than today. So it's like one day and I got the whole swoop. So anyway, I'm a business developer these days, and I'm in charge of the European market and the Middle Eastern market. I do know sufficiently the technology to speak about certain developments, and I will go ahead and start my presentation. Okay, it's coming in 1 second, please.
It's coming up.
So while we're waiting on the presentation to be available to you and you can see it, what I can say is that I will be going into the agenda. I will be going into the technology. It was a little bit I wouldn't say very difficult, but quite challenging to put together all the technology that will be relevant to this conference. So, without understanding or without actually listing out all the technologies, I would like to present to you a little bit the company who's behind, all these things that we do. Control L. Control L. Yeah. Yeah. We make it a little bit larger so that we can see one page at a time. Can we do like a full screen view now? Okay. Can we go to the first page, please? Okay. Thank you very much. So I would like to do an introduction of the company, and allow me to do that because it will give you a reference of who we are, where we came from, and how we got where we got today. I will also talk about some of the core technologies we cover, including semiconductor, display, LED and OLED technology. And the last portion of this presentation will be about the solar technology. And this is probably more relevant to our partner. So go ahead to the next page. So basically, Jusong is a South Korean company, and we cover these three basically core technologies. One of them is semiconductor. The other one is display, including the LCD and the OLED technology. We did a lot of TFT in the past. And we have, of course, a division of solar. As you can see, I just wanted to put like a small picture on the side, on the right-hand side, as you see. These are some of the, some of the PCBDs that we use for display, just for display. And we have about like, I would say about 700 or 800 chambers in mass production today. Go to the next page, please. So just, quick company overview. So the company was created in 1993 by Dr. Huang. You see his picture in the middle of the slide. And in 1993, believe it or not, or before, shortly before, South Korea didn't have any semiconductor technology whatsoever. And South Korea resembles, in certain ways, outside the realm of geopolitics, it resembles very much Poland. So I do see that in Poland there is a huge opportunities to go into these technologies. So everything was brought from either Japan or the United States, and it was basically copied. But then the government of Korea decided to create and invest in the semiconductor industry. So what they did is they, of course, helped a lot of companies, small and medium-sized companies, and they asked them, the strategy was to create an ecosystem for this type of industry. Our company, Jusong, was the leading company in Korea to actually start looking into this ecosystem. So we are very proud to state that we are one of the companies who really created the environment and the ecosystem for the semiconductor industry. In the company, we have 4 divisions. We have the semiconductor, we have display, we have solar, and OLED. In the OLED, as you know, there are 2 parts. There is the display, OLED, and then there is the lighting display. And we have invested so much money in the OLED lighting because it presented some very good opportunities in the future. And we have also some tools for the OLED display. Our company is based actually on R&D. So if you look at the company, we do a lot of research and development, and that's what gets us to the market, and that's what gets us to our clients. So far, we have invested, since the creation of the company, we've invested close to $1 billion in research and development. We have about 78, we have about 2, let me go back to this IP, because it's very important. We have over 2,000 intellectual property or patents registered in different divisions, whether OLED, solar, or semiconductor. And we have 78 clients. Now, this is very important. We're not a business to client type of setup. Our end clients, like they're not the consumers. They don't see us. But everything maybe you use today in your life, there is some tool, there is some process behind it that has been done in one small portion by Jusong. As the semiconductor industry, or these technologies are quite complex and require a lot of tools, a lot of processes. As you can see from on the right-hand side, these are some of our clients, and we don't have too many clients because building fabs and going into this industry is very capital intensive. We're talking about hundreds of billions, and then you have to renew them every year to stay on top of the technology and the products. You can see we have some that you might recognize, like TCMC, IBM, NXP, LG Display, Global Foundries. We used to have a lot of business with Samsung, and we worked with some companies locally here in Europe. We have 12 subsidiaries because everywhere we go, usually when we have a project, we try to be as close to our customers as possible. So we implant or we put some offices in the local regions where we are. If you take a look at our structure of human resources in the company, you would find that more than 60%, actually it's around 65 and more, 65% of the human resource that are working for Jusong are exclusively dedicated to R&D. So they are not involved in a lot of manufacturing, they're not involved in administration. We have a very, very thin team of marketing because we don't need to do a lot of marketing with these big guys that we work with. We have a lot of recognition within Korea and outside Korea with the big companies such as Samsung and so forth. So go to the next slide, please. I'm going to increase the pace a little bit. So this is just a picture of our campus. So we basically had the one on the left-hand side is our Gwangju campus, and this is the one we started with. It's quite big. And recently, just about, I would say, a year ago, we built and we installed equipment in our other R&D center, which is a little bit further down. Okay, move on. This is briefly an overview of where we are. So basically Korea, then we have some offices in the US, we have offices in Europe, like Germany, France. We have some representatives and subsidiaries in different areas also within the Middle East and Asia. Okay, move on. So this is just, to go into a little bit detail about the structure of our company and our investment. And this is very important because we take innovation at heart. If we don't innovate, if we don't do research and development, then we have no business. So basically, over the years of the company existence, we've spent about, like $1 billion worth of research and development. Again, employee-wise, we have 62% of people, they're exclusively dedicated to R&D. And we have a bunch of intellectual property. Move to the next one. Yeah, you can keep moving. This is just more detail. So this is just to show a little bit history and of our innovation and where we're going. This is not the latest. This is not the most updated, as it stops around 2015 to 2019 maybe. We work in the semiconductor. We work in both worlds. We do a lot of we do a little bit of logic, but we do also a lot of digital, especially in the memory area, and that's where our equipment. And this is our, this is where our greatest impact on the technology, because it's so complex, it's so demanding. Our clients, they want us to provide them with tools that can actually increase the density of the memory, lower the power consumption, and do it as quickly as possible with tools that do not consume too much real estate space in the fab. Those fabs, especially in the memory fabs, they are class 10,000 or more. So every inch of real estate counts. So if the tool doesn't perform within the specs of the client, they just ask you to take it out. Move on. So with the semiconductor, I just wanted to present to you some of the tools and processes. And, you know, because this conference, there are a lot of scientists, there are a lot of researchers. I'm sure they can relate to some of the processes we do. So basically what you see on the top, you see the deposition tools, CVDs, different types of CVDs. And in the middle, you see the tool. At least you get an idea. But the top portion is probably the most important because that's what we do. That's for a professional, when he looks at the process, he understands what we do with this. So we work with different things, different materials, different processes. Like, you know, for example, you know, high K. We work with deposition of, you know, doing STI, doing poly, doing different things. The one that is circled in the middle, when we talk about the local space divided plasma, those are very, very recent and very advanced tools, and they do so many things for the industry that are, you know, we sell them almost to a lot of our clients. I will talk a little bit about these things because for some professionals it makes sense when they see what I'm going to show them. Go to the next slide, please. So basically everybody around the world has been building these deposition tools, different types, different processes, different sizes. But what we have realized in recent years that when you do such things, you cannot do only one thing, you do multiple things that are correlated. So if you start with one thing, you got to do the second one, the second step, and the third step. Because of the real estate of these sophisticated fabs where we put the tools, our customers, they ask us, how can we combine these processes in one smaller tool that can do what we want and give us the throughput and the yield we're looking for? So we came up with this idea of the LSP, what we call LSP technology, so local space plasma. And then underneath it, that's the global one, underneath it we have two types depending on what you want to do with the tool. You do memory, you do logic, you do certain other things, microprocessors or processors. Then you get into the time space divided plasma or the space divided plasma. The most important thing here, because I cannot go into the details, but those tools, they provide the best interface control, the incubation time control, the low thermal budget, which is very important for a lot of processes nowadays. And the system is very easy to set up and very easy, you know, to function. Very easy also to integrate with other processes that you have on the line, the production line that you might have in your fab. One of the things we do is the, and I will speak about that in the next slide, but go ahead, please give me the next slide so that I can see. Sorry, I don't have control of the slide, makes it very hard for me. So, you know, when you deposit things on a substrate, when you deposit, you know, some materials on the substrate, and depending on what you have already deposited, there are some sensitivities of that material. The material can be sensitive to high temperatures, it can be sensitive to an electric field, it can be a combination of many things. So what we do, and this is probably we are one of the initiator of this idea, is to use actually the electric field sideways so that we don't damage the substrate. It's very important. And some of the things that that you see on the right-hand side, for example, for this specific tool, the time-space divided tool, is it has zero plasma damage, because in the past yeah, people use, you know, CVDs, they use plasma, of course, to make the depositions, but then they have some kind of a degradation, sometimes even, you know, an impact on the substrate or the materials that have previously deposited. So this is fantastic for the production, guys. Please go to the next slide. That's good. So some of the advantages of using these tools, as you might imagine, so it's a number one is the thermal budget it can be very low. I mean, we're talking about 50 C, and that will be enough for a lot of applications to deposit different materials. The film, you know, because we are a thin film, we are a deposition company. This is our very core expertise. Step coverage, stress control, and even the etching is very good, and the rate is very good. Please bear in mind that these tools are for mass production, so they have to be very quick. They have to have high productivity. So what we do is, like in the case, for example, in the case of a CVD process is quite fast, but there are some processes where it takes more time because you need to go into a little bit more complicated depositions. So we use ALD tools. ALD tool is very slow, and everybody knows that. But what we have done with this tool, since we have like a rack, and this is, you know, a little bit older version, so we can, you know, the newer versions, they can even tackle, you know, much higher production rate. It's like the rotations, when you put all your wafers, you put them on this disk, and they rotate at very high speed, and the deposition happens, whether you're doing a CVD deposition, we're doing ALD deposition, it goes very fast. And that is very important for the production people, because it might take 3 months or 4 months to produce like a device. And you have to go through so many tools and so many processes. Any second you save in your process on your tool is worth millions and millions of dollars for the producers. So the last point, number 6, is the combination. It's like, think of it as a Swiss knife. You can do many things with it. You can do an ALD, you can do low pressure CVD, you can do plasma enhanced CVD. It's one tool that can be put, you know, in a very small area, and it can give you all this capability, which you will need regardless of what you are doing. Most likely you will need all these processes in your application. Please go ahead to the next slide. So here I just, you know, showed, you know, very quickly some of the tools we have in the R&D lab. We spend a lot of money on R&D, and we spend a lot of money on our people, but, you know, we want to make sure that everything that gets out of Jusong is fully tested and working to the specs. Some of these tools also, we use them for demo, because that's the first thing that the customer asks. You know, they will send us, you know, like some wafers, and then what we do is we just, you know, go through a demo process, and then once the things look good, then, you know, we start talking about the equipment. So this is just a snapshot picture of where we put the tools for semiconductor. Keep going. Again, the same thing. This is, you know, like semiconductor display. This is a display. I need to go a little bit quicker because I don't have a lot of time. Okay, so this slide is probably more relevant to our conference. So, number one, either in semiconductor or other in solar, we do not touch something that doesn't have an innovation premium. It has to have an innovation premium, right? Because we invest and we spend so much on R&D. We have to be competitive. We have to distinguish ourselves and make something new. That also guarantee for us the window or the production window. So we get in upfront, and that's how we can actually raise the interest of our clients. If we look in the solar, Yes, at one point we did thin film, we did flexible thin film, we did building integrated, we did vehicle integrated. One of the things we did is the heterojunction, because it had, when we looked at it, it had a very good innovative future. So we jumped on this heterojunction technology, and we have actually delivered equipment and even did some technology transfer to Europe on the heterojunction technology at the mass production level. So a lot of people, they might say, okay, we have a small lab in university, or we have a small lab in a research center, and they work on a very, very small areas. You know, they can be even centimeters, you know, few centimeters, squared centimeters. So when you are working in that environment, it's completely different from production, mass production, because there are so many other things that we have to take into consideration, right? So these tools are mass production tools for heterojunction technology. Now, since we realized that there is a limitation in the power conversion efficiency for heterojunction cells, we decided to see what can we do to increase the efficiency. So, like for example, today I heard Saint-Gobain, I heard also other companies in the glass business. They're talking about like the zero building energy. So basically, if you have a building, which is a great idea because you can cover a building, it has a good surface area, you can cover it with glass. The glass needs to be smart, needs to be isolating all the heat or the thermal things, either, you know, during winter or summer. It needs to create some power for the building. That's a great idea. But this technology of PV in the cell, that's really where we think it contributes to the idea of this glass panels, because that's where we do the conversion of the sun radiation into electrical energy. So the cell is actually the heart of this, you know, like smart buildings with panels and glass and so forth. So we started looking at the perovskites. Many people have been looking at perovskites. Perovskites, of course, is a material that we can find readily available. It's not rare. It's not very expensive, but it comes with a slew of problems. At the beginning, when people started, you know, building cells using perovskites, they would just look at they will build it, they look at it, they check it. Whoa, I got 3% cell efficiency. Great, super. That means, you know, we're succeeding. They turn around, they go get a cup of coffee, they come back, they check it, and it's zero. It's gone, or it changes. So because it's the material being used has some properties that are very, very dynamic depending on the condition and the environment you are in. So basically what we did, we said, this is a good innovative thing. Let's look at it. And then we had some partners also who were really pushing us towards this. I will go into the next slide and I'll tell you a little bit more about perovskites. So this is only equipment, so I'm going to skip this. We are an equipment company, so go ahead, please. Keep going, keep going. Okay, so I get to this. I'm sorry to go back to the basics, because some of you might already know all this stuff, but it's good to have a reference point and where we came from and why we started looking at this. So basically, when we looked at this perovskite was a very good candidate for the simple reason that in 4 years, we have gone from 3%, around 3% efficiency, to almost 20% efficiency. So there is a huge opportunity there to do something about this. In only 4 years, we were able to go from very low efficiency to some very competitive efficiency, even with the other materials that we use, the silicon. So we looked at it, and then we realized that there are problems. There is problem of cost, there is problem of efficiency, and then there is problem of stability. And all these three things, that's what they call this is not my naming, it just got it from the research out there, that's the golden triangle. I call it the tricky. It would have been better if we named it the tricky triangle, because the thing is, if you focus on one area, like, you want to increase efficiency, you're going to impact the others. They are so mutually interdependent. You try to lower the cost, and then you're going to end up with low efficiency. But what we have realized, that the biggest problem really into solving this dilemma is the stability of the material. Stability means how long this solar panel that we are building, or how long this solar cell is going to last. If you sell a solar panel to your customer, you want to make sure that this solar panel will be at least operational at 90% or 95% for like 20 or 25 years. That's what the customer wants. You don't want him to change panels every year. So this is what we did then. So we said we're going to look at these three things. So so let's go to the next slide, please, which is good. So we looked at this. For some of us, we already know this. So I apologize to the people who already know what the perovskite structure is and the crystal. So basically, it presents itself as an ABX. We call it the ABX structure. A being some material, B being some material, and X being some material. So I listed out some of the things that we work with. Some of the materials we use are organic, some are inorganic, and what the industry is realizing is that sometimes it's a good combination between organic and inorganic is probably the best. However, we need to do some extra work to protect the cell. So some of the advantages of the perovskite, as you can see, besides, it's a good technology that's going to propel us, into higher and higher efficiencies. I think one of them is that we can exceed the limit, or the theoretical limit, and maybe even a practical limit of the crystalline solar cells. And this limit has been set by two scientists. We call them Shockley quasar limit. And basically, all the radiation that comes from the sun, if you try to capture it, all of it, then you would have 100% conversion from the radiation to the electrical power. The problem is there are some losses, and then you cannot capture everything. Shockley and Quasar said, based on the silicon, you cannot go beyond 31%. And they made the calculation, and everything checked out okay. Now, so how do we increase this conversion efficiency? This is probably one of the ways that we are realizing that we can go beyond the Shockley quasar efficiency by combining two types of technologies, combining the heterojunction technology, which is based on silicon, with the perovskite material, another cell. So we're building two cells, one on top of the other. One will allow us to capture a piece of the spectrum or the radiation, and the other one will also allow us to capture a little bit more. And that's the name of the game. I will not bore you with the challenges and the solutions that we have found, but I go to the next slide if you don't mind. So what is the current state of perovskites right now? So if you look at this, and I'm going to go a little bit slowly on this one, because everything is very important on this slide. So basically, the bottom, if you look on the left-hand side, you see the top. That's the perovskite cell. So in the middle, what you see like the gray stuff with the granular like this. That's the perovskite material. On the bottom, you see the ETL, which is the electron transfer layer. and the top is the whole transfer layer. That's the encapsulation. And then we do the same encapsulation for the crystalline or silicon-based cell. We have to make sure that we have a TCO in place to conduct the electricity laterally, etc. When you see that picture on the left, the heterojunction cell is not shown, just so that we can have a very good blown out view of the perovskite cell. So basically what is happening is that some of the problems we have seen, and they gave us a lot of hard time, is the interface. So every time you take a material and you put on top of it, or in the bottom you put another material, then there is some dynamics that takes place. It can be a physical dynamics, it can be chemistry, it can be especially chemical dynamics between the molecules, between things like that. So what we try to do, we try to eliminate those dependencies on the layers. So the current status right now is we're looking at a power conversion efficiency as of today of 30.5%, okay, on the cell level, with an open circuit of 1.33 volt, which is a huge compared to the crystalline. Crystalline is around 700, 720 volts, right? This, I mean, 0, millivolts. So this one would be 1.33. It's quite sizable. And the current also is, the current density is very high. It's 25.4. That's pretty good. With a fill factor of almost over 90%. So that cell is working good. So we started, there are some scientists, they started initially with the structure called, or with the material called methylammonium, but methylammonium is very unstable. So we started looking at formamidinium, and by combining the two, we can stabilize the molecules and the structures enough so that we can have a panel that lasts for 20 years and beyond. So this is the state of the perovskite at this point. I put in the bottom why we think we can close this, because this ETL, what you see there in blue and yellow on the cell, the ETL and the HTL, it's the same thing that we deposit for the OLED, for the display. Because if you have a TV in your house, especially if you have an OLED TV, which is very, very sensitive to humidity, oxygen, things like that, which happen, right? So if you do not encapsulate and protect the screen that is inside, if you don't protect it very well, it will go very bad very quickly. It won't last you probably a few days. So we do the same, we use the same principle. So we have equipment that actually has been adapted from the display and is being used right now for the perovskite cell. Go to the next slide.
Ali, will well past 30 minutes mark, so please make it a little bit faster.
Okay, let's go. Let me choose. So this is technology, so I'm going to skip this. Go ahead. Okay, this is important. This is very quickly. This is our roadmap. So this is how we think. A goal without a plan is just a wish. So if you look at this, behind it, there is a huge plan of how to get from 2019 to 2025 and what we are doing. So on the top, you see heterojunction technology. The bottom, you see tandem technology. Actually, what we have done so good so far with everybody else on the market with heterojunction technology, but we are reaching the threshold of heterojunction technology. So we need to add perovskite as a tandem cell. When 2022, 2023 kicks in, we're looking at 35% cell efficiency, and beyond, we're looking at even 40%. That's our plan. That's our goal for the future. In terms of equipment, on the left-hand side, we have a turnkey line solution for heterojunction. Then in the middle, you have the perovskite cells making, and the final part, we don't do print and screen. Go to the next slides. I will do. Okay, this is only things that we have been working on in the automotive, because we have also combined OLED with PV, and we can do these things, and we're working with some of the companies that you know in Korea. Keep going. And Germany. Keep going. All right. Same thing, you know, with OLED lighting. Keep going, keep going. Keep going. Keep going. Keep going. I want to do the last slide. This is probably, you know, I'm going to try to make it as short as possible. So a lot of people ask me, why do you come to this country? Why would the Korean want to come here and invest here and work here and develop partnerships and relationships? Well, those are some of the reasons we can think of. So from a partner perspective, we are convinced that we're picking a strong industrial partner who has experience in an industry, whether he's doing glass, whether he's doing PV. At least he has the logistics, he knows what he's doing, he knows the business, he knows the market, how to sell, how to manufacture, and all this is very important to us. So, you know, the first slide, the first window, you see that, you know, we have an industrial partner, and we're thankful that we have met ML System, and I think, you know, it would be an ideal partner. They have experience in BIPV, which is a plus, so we don't go through the basics again. They have a captive market. But what do we mean by captive market? They can consume what they produce. They don't have to sell the cells themselves. They can. But what they can do is they can just make panels using glass, using also their technology, which is complementary, or even, you know, sometimes, you know, adds supplementary, like, you know, the quantum glass, and we can sell the product at that stage. They have R&D. I was very impressed yesterday when I saw the buildings. They're very modern. They're very spacious. The equipment is there, all the equipment to do the characterization and the metrology. So that's why I said this strong. The country is very good for us too, because I think there is a willingness, at least from our side, from outside, when we look at Poland, we see that there is a willingness to decarbonize Poland, right? They have a lot of old fossil fuel sources of energy, like coal. They want to get out of this one. Of course, they have to find all the appropriate solutions. What that means, it means that they will invest money with the partners. The last point I want to make is about the cost of doing business. Cost of doing business in Poland is very efficient compared to where I operate. I've seen France, I've seen Germany. I love those countries. I love to operate there, but the cost of doing business is very, very high for these reasons. The market, I think, you know, our partners are willing to go to any market. They're willing to follow us wherever we go. We can go to the Middle East, we can go to the US, we can go to any market, and we're happy with that. And for that, I will conclude my presentation. I am very, very sorry. I extended it. I knew I had only like 20 minutes. Sorry about that, Bartos. Thank you very much.
Thank you, Ali, for riveting presentation. I'm sure there are going to be many, many questions, and of course for your kind words for the ML system. I'm not sure we have time for any questions left, so please feel free to apply questions both online, via email, or on our social media. We will make sure that all the questions are forwarded both online and from the participants in here are forwarded to Ali personally. We'll make a little bit of shift in the order of the presenters. Our next presenter is going to be Bartłomiej Kras, and next Monica Alleman, because of the scheduling of Bartłomiej. Bartłomiej Kras is the CEO of the Impact Clean Power Technology Company. He holds a PhD from Warsaw University Technology in the field of fuel cells. He worked in the field of energy storage solutions for e-mobility for the last 16 years. He's a specialist in the field of design and application of lithium-ion battery systems, for which he has supervised many application projects with Citroën, Bosch, or Solaris. Today, he's going to be presenting presentation titled Consideration of Battery Energy Storage Size for PV Installations. So, Bartłomiej, the floor is yours.
Okay, thank you very much. I will be speaking in English, but presentation is in Polish. So, może pan jakoś powiększyć to też? Okay, Impact Power Technology is a Polish company which has been founded in 2005, so already 16 years on the market, and we are leading manufacturer of energy storage system for e-mobility and stationary applications. We are located in Warsaw area and have a facility able to produce more than 400 megawatt hours of lithium-ion batteries at present stage. We are focusing on development of the modern battery pack systems, either for the e-mobility and for stationary applications. So we are right now employing 230 people in Warsaw area, and we plan to expand and build gigafactory in Poland for the battery packs up to 2 gigawatt hours. The investment is planned for 2024, so it will be a huge facility. We started 2005 making mainly e-mobility projects in the past, developing different batteries for heavy duty industry. Now we are mostly building battery packs for the electric buses. And in Poland, practically 95% of electric buses running in our cities are equipped with our batteries. So practically all Solaris buses, all Autosan buses, and Ursus electric buses. But we are exporting a lot, so we have very strong presence in United States, Western Europe, but also in Far East. Except battery packs for the heavy-duty buses, we are also exporting batteries for the mining applications, for the special vehicles in mining applications. And our new activity is stationary storage devices for the PV applications. Just coming back to e-mobility, we have more than 6,000 systems sold worldwide for different heavy-duty vehicles, including buses, but also heavy-duty AGVs. In Poland, more than 300 buses running with our batteries, and except Poland, around 600 buses and trucks also using our batteries worldwide. So our batteries already clock at 70 million kilometers worldwide. So typical product that's heavy-duty batteries homologated for use in the buses and the trucks. And please continue. And now we are entering the energy storage market for PV installations with the product destined for the three sectors. First sector is the home storage, and here we have developed the product which called Fola Energy. It's 4.4 kilowatt, 48 volt battery pack for home PV installation. We have just launched the production line in our facility in Pruszków for 30,000 such battery packs a year. So we are prepared for the Mój Prąd 4.0 programs. The second product is destined for the business, for the modern supply of the industrial facilities, so combining PV and batteries together. And later I will be explaining the business case about it. And the last product is dedicated for large energy storage and large PV farms. When we have today developed a lot of such installation in Poland, but practically none of them is equipped yet with the energy storage, and the future solutions for our power system will require also placing larger battery pack systems. We have several installations done in Poland already. The very first one was made for Inogy in 2016 as a pilot installation of rather small power, 30 kilowatt hours. But then we commissioned 2 more large installation. Then the next one is the installation which start to operate this May. It has been developed for the PKP Energetyka, and this large battery pack system directly connected to the catenary grid for supply the power for the Pendolino trains, and to keep the power inside the power lines. So it has 5.5 megawatt power and around 2 megawatt hours of the capacity inside batteries. And the latest installation commissioned in June this year. This is the one of the first installation in Poland, which is battery pack directly connected to the PV farm located south of Poland on the Góra Żar. There is a PV farm belonging to PGE, and we have installed there the energy storage 1 megawatt hour, which now started to operate this June, and PGE is planned to make test and validate. Now I would like to speak very little about how to size energy storage to the PV installation. So this is very big common problem, because we have many factors of choosing the right PV installation and choosing the right energy storage. So this is case from one of our customers which came to us and asking whenever we can size for him PV installation and energy storage, battery energy storage. And his yearly consumption is 7,300 megawatt hours yearly. So this is the chart when we are making a lot of calculations and finding which size of PV installation and which size of energy storage would be the best for him. And the most important factor is the self-consumption of the customer, and also the prices of the energy which could be sold to the grid, and then the prices of energy which has to be bought from the grid. As we know, in Poland we have right now changes of this values. So this is very sophisticated calculations, and here we are showing different variants of the different PV. So the green bars, it's the power of the PV installation. So from 400 kilowatt hours up to 15 megawatt hours for this particular customer, and judging that investment in 15 megawatt hours is very huge and will never pay off. The best solution could be choose something in the middle, so around 2.5 megawatt hour of PV, and then add larger energy storage. This is one of the case. We also making more sophisticated installations, because we have 4 different factors we have to take into account for such applications. So define level of self-consumption. Then the second is net present value calculation, so how fast this installation will be pay off. Then the customer has also limited capex, so not everybody wants to invest bigger money. And of course, whenever we have possibility to connect to the grid, or this will be only off-grid installation. Especially now in Poland, with our situation with our grid system, the connection of the PV farm to the grid is really problematic. So having those calculations taken in mind, so we can for example, for maximization of NPV value, we can provide that the PV farm should be at the level of 1.9 megawatt, and in the same time energy storage, so battery storage, should be at the level of 0.8 megawatt hour. So this is the optimum parameters for this particular business case when we have on-grid installation, and we want to maximize NPV value. And on the next slide, we have show the results of our calculations. I just said it's just one of the business cases we are looking. So on the left side, it's the case that left side of the table, the company wants to install just the PV. So PV at a relatively low level, 0.6 megawatt hour, and then factor of self-consumption would be quite high because it's of course its yearly consumption is 7,300 megawatt hours. But in this small PV farm, this installation is almost fully working on internal auto consumption, but the factor of auto consumption is just 9%. So adding the energy storage, of course, will increase the capex. As you can see, these are values taken from the mid prices on the market. And also increasing the PV to 1.9 megawatt hour and adding this energy storage 0.8 megawatt hour can increase the factor of self-consumption by 20% more. And as we can see on PV, on NPV value, so the pure PV on the red will pay off between 4 to 5 years, and the large installation with energy storage, the payback time will be a little bit longer, up to 9 years. But then the incomes will cross the installation without energy storage. All those values are taken into account without any subsidies, any government subsidies. So this is typical business case when we don't have any government subsidies. And of course, we have a very dynamic situation in Poland regarding the system, the net metering system, and the prices of the energy. But based on the latest assumptions and informations we can get from the regulators, in 2021, the average price we could sell the energy from the PV to the grid was at the level of 252 zlotys per megawatt hour. But we assume that for 2022, with the new net metering values, the energy which the user will have to buy will be at the level of 800 to 820 zlotys per megawatt hour. So it's 4 times more than they selling. So it means the pure photovoltaic installation is becoming less and less profitable for the users. So also we assuming that battery energy storage added to the installation can increase auto consumption, which allows to save money in such an installation. And then we try to make a very brief calculation, and please show the next slide. What is the payback time if we add energy storage to the home PV installation? So this is the second business case. We can assume that we have 5.8 kilowatt hour peak, which is average Polish PV installation, and with 5 kilowatt inverter, and we add 5 kilowatt hours of energy storage. So we have around 6,000 kilowatt hour per year production, and of course we have this pricing with which probably will appear because this 800 zlotys per megawatt hour is predicted price. We'll have to buy energy from the grid for such an installation. But having additional energy storage, when we can store energy and use them for auto consumption, it will increase auto consumption of such installation by 20%. And having the cost of the installation, we have yearly savings by around 680 zlotys per year, which gives the payback time for the combined installation PV and energy storage at the level of 11 years. So it's almost 2 times more than the pure PV installation today with the present factors. But this value doesn't count the subsidiary. So if you would have a business case that government is not supporting any PV installation or any energy storage or any batteries to the PV installation, the average payback time would be 11 years. So of course, if you add subsidies, which yet nobody knows what the values will be and whenever they will be, this payback time could be shortened. Of course, the expected lifetime of the battery will be 15 years and more or less the same like the PV installation. So I presented shortly the two business cases for the larger PV farm and industrial application and the household PV installation with the batteries. And this is just showing how complicated the calculations are and how many factors we should take into account to really answer the question whether we need battery energy storage for the PV installation or not. So this is all what I wanted to explain, and we invite you to contact our company for all those sophisticated calculations, and of course we are exactly in the middle of decision-making process by our government whenever to subsidize battery storage in the next year and make these calculations much more profitable, or postpone this for later. So I would like to just present the situation without any subsidy. This is the situation on the Polish market today. Thank you very much.
Thank you so much, Bartłomiej, for the interesting presentation. I'm sure for many PV systems designers, this is a real game changer. Unfortunately, we do not have time for further questions, but make sure to post them to us so we can forward them to Bartłomiej. Thanks again. Our next speaker is going to be joining us remotely. Please give a welcome to Monika Aleman. Monika, can you hear us?
Yes, I can hear you. Can you hear me?
Perfect. I've had the privilege of working with Monika on the silicon solar cells in IMEC. Monika received her PhD for work in the field on silicon solar cells from Fraunhofer Institute. Then she moved to work on the top efficiency PERC cells in IMEC, where we met. Currently, she's the head of research and innovation at Becquerel Institute in Brussels. She's going to be sharing with us the details of SerenDPV project for the smooth, reliable, and dispatchable integration of PV in the EU grids. Without further ado, Monika, the floor is yours.
Yeah, thank you, Bartek. I'll be a bit quick as well because of the time. First of all, I wanted to thank you for the invitation. And yes, just one slide to present the Becquerel Institute, where it's a company where I'm working. We are a small company located in Brussels. We're providing a strategic advisory and consultancy, as well as work on applied research for techno-economic analysis on PV systems and the whole ecosystem. So these are some of the partners that we've been working with, and also the projects that we're involved in or have been. So if I go straight to what's interesting for this session, which is SerenDPV, it's this project that started in 2020, and it's going to be going on until 2024. It's 4 years, 12 million euros, and we have 19 partners in the project with a lot of different scopes. We have universities, we have PV developers, we have Ingetim and Segasa, which are making inverters and batteries. We have companies like QPV, Lucisan, which are making O&M and modeling. And we have companies like Light Systems, which are quite interesting because they work on optimizing the consumption of users at residential areas, Solaris, which is working on modeling and so on. So before I introduce SerenDPV, I think the most important question is, why are we doing this project? And the main thing is that we see that the cumulative PV installations are rising. This hasn't stopped. And so yearly installations for the world are at the moment at over 140 gigawatts. So we know that this is going to become a much bigger thing in the future in the energy grids. If we look at the context of solar PV in Europe, we see that depending on the countries, there's a big difference in the application of residential PV or utility scales, where you have countries like Romania, where most of the PV applications are utility scale based, or in Belgium, where it's more residential PV. So one of the main reasons while we were working on this project is because when we look at one of the studies which was done to understand the levelized cost of electricity, we saw that after a sensitivity analysis, one of the main parameters affecting the LCOE was not related to the technology, but the risk that is, let's say, assumed by financing institutions for PV installations. So if we go further, it's like, okay, we have this WACC, which is representing the risk. The question is, how can we reduce the WACC, basically increase the trust in PV production and in PV systems for financing companies? And what we have done, or what we plan to do in Serenity PV, and what we're doing is working on quality control, component reliability, system reliability, energy yield assessments. And the target is to increase the lifetime of PV systems and components, and especially increase the performance of the PV systems. So another issue which is relevant for the project is basically that the PV systems are becoming more and more diversified. So in terms of modeling and yield modeling for such systems, there are some differences that need to be taken into account. We have some floating plants in France. We have more and more solar PV installations, which can be looking like this, or can be on greenhouses. There's BIPV. We have plants in the desert. Then if we look at the total penetration of PV for the different countries, we see that at the moment we're in the EU in average about 5%. This is for 2019. But the idea is that with the increasing of the penetration of PV, this is going to create a bigger challenge for the network. And the targets, in order to maintain the Paris Agreement, has been calculated by the Lund University in Finland. They expect that solar PV should be representing about 69% of the total electricity production. So this is going to be huge, basically, if we want to maintain the carbon agreements, the Paris Agreement, sorry. So what happens is like, okay, ideally, when we do the integration of PV in the grid, we would like to be able to define exactly what's going to be happening in terms of the load management, so that we can adapt it to the PV production, and also we can use storage systems. In practice, of course, we need to do a lot of forecasting to be able to do this, because the precise predictions of PV production are very, very important when this would represent the biggest part of the electricity production in Europe. So one idea that, of course, people are working on is considering the mini grids and collective self-consumption, where you would have, for example, a set of houses connected to a battery system, and these ones could be connected to one another, so that the consumption and the production could be optimized, not just at a house and residential level or company level, but also for a small local energy market, for example. So if I take all these points and we bring them to Serenity PV in the project, what we want to do is then, of course, to increase the reliability and the performance of PV systems. We want to decrease the LCOE. We want to increase the profitability of PV generations in the grids, and we want to increase the stability when the PV penetration is higher. And at the end, we want to lower the variance to enhance the development of the PV sector in the EU. This is what the Serenity PV is looking to do. So we have developed 7 axes to be able to do that. I'm actually going to go one by one later, so I'm not going to spend much time on this slide. Because here I'm explaining a little bit each one of them. The first one is about simulation. So here what we want to do is improve all the modeling parameters and modeling tools in order to be able to give a better reliability about the performance of the PV systems and increase the profitability. So yes, afterwards, of course, I can send you the slides. You can look at the references. Sorry. The second working axis is about monitoring. Yes. And image-based fault diagnostics. In this case, what we want to do is improve the monitoring of PV on the field. So for this, we're developing some soiling kits that can be installed at PV plants. We're improving the modeling of PV plants, which might be covered by soiling issues. And the whole point about this is just to improve the reliability of the energy yield assessment and also to reduce the things that are reducing the production of the PV plants. Then we are putting in place quality control equipment and procedures for PV components. Here you can see some examples of what we can do in some of the universities like at SEBA. They have testing sets where they can very well define what are the failure mechanisms of the PV plants. And then the idea is afterwards to introduce quality control procedures to the then we have an axis which is called forecasting, and here we have Solaris and Fraunhofer, which are very active in this point. The idea is that you start from numerical weather predictions, then you go to looking at the satellites for the cloud motions, so that then you can use machine learning with real-time PV power measurements to improve the forecasting mechanisms. And then what you can see at the bottom of the slide is basically how it works in the energy markets, where you need to have different type of predictions. And depending on these predictions, they have different implications in terms of the financing of the projects, of the forecasting, basically. Then we have one axis, which is about looking at new business models. And as I mentioned before, you have new companies which are popping up, like My Light Systems. What they propose is a service to customers who can optimize their self-consumption by giving access to their PV production and their electricity consumption or the electrical load at their houses to this company, so that they are switching on and off some equipment depending on when the PV production is highest to reduce the exchange with the grid. And then on the other hand, you have companies like Next Kraftwerk. They are a virtual power plant, which is basically working with a lot of different PV plant owners, and they are handling a share of their PV production to put it at the market and to be able to provide ancillary services for the grid. So basically this represents a different type of making money for the system, because then they're providing flexibility to the grid, and this is very important. Then we have one axis, which is about the technical constraints for integrating large volumes of PV in the grids. And here I thought this was quite interesting. And this is something that we have been also learning from the project, that today we have a situation where most of the energy is being produced in a centralized way. But in the future, basically, this is going to go from the transmission lines in the centralized way to the distribution lines, where you have all the small systems which are producing electricity everywhere. And this is something that needs to be handled in terms of data. So we have basically one whole working package, which is about understanding how to improve the architectures for data transmission. And then depending on the country, so in the EU, the regulations are very different at the moment. In Germany, they have already quite some mature processes for this data, but in other countries, it still needs to be developed. So we're looking into this. Basically, the idea here is that you would have different economic applications in terms of power purchase agreements or system service and billings and so on. In terms of technical operations, you have monitoring and self-consumption and software updates, and then you're going into the network control, where you can, by gathering all this data together with companies like Next, for example, propose some curtailment or adapt the parameters and then the state estimation. And in the future, the idea is that you'll be able to do some plug and play and maybe work with cellular networks and resilience networks for the managing of all these distributed PV systems. So I think with that, I am done. I'm sorry if it was too quick. I need to leave very soon. So yeah, this is basically what we're doing in SerendiPV. You can go to the project's website and look at the results that we have been gathering. As I mentioned, it only started in 2020. So yeah, there's still a lot of work to be done.
Thank you so much, Monica, and sorry again to keep you waiting. It was riveting presentation. I'll make time for one question. It's going to be from me. What do you need to do to hook up your PV installation to the Serenity PV projects to contribute?
Sorry, what do you need to do to hook your PV installation to the project?
Is it possible, because we are on this of the PV presentation, to contribute with the fully operation PV installation on our buildings that we have a monitoring of? Can we do that?
Yes, of course. So we have one working package, which is about a collaborative platform, where the idea is that we can work with different people who have installations, and then they can share their data. And then for the time of the project, we can offer some forecasting services if this is interesting for you. And in exchange, basically, what you'll have is a bunch of research institutes and companies analyzing your data to be able to use it for the project. So yes, indeed, this is, if you have production data, this is definitely interesting, especially for BIPV plants and innovative plants. For sure. Then you can just basically write to me or write to Eduardo, and we'll figure out a way to contribute.
Perfect. Thanks so much. We'll make sure we do. And for all of you who might have questions for Monica, please make sure you post them on the social media or contact us via email. Thank you so much, Monica, again.
Yeah, thank you. Thanks for the invitation. Goodbye.
Bye. So I have a little bit of a news as well. For this session, we have a decision on selecting the best speaker, most favorite speaker. The award goes to Ali Said. So give it up for Ali. I think we have a little token to give away. No, okay, thank you. Right now, we are going to have a 5-minute break, and then we come back with the next part of the session, in which Marcello Passaro from Kiva Sermet Italia and Antti Tulvanen from NDAS Finland are going to be joining us online. Thank you.
To po prostu. Jakby nie było włączone. Jasne. Sekundkę. Zaraz sprawdzimy. 40 sekund. Może pan coś powiedzieć? Fajnie, dziękuję. Mogę pan...
Teraz działa.
Hello and welcome again in the second part of the panel on modern photovoltaic energy systems. For those newcomers, my name is Bartosz Zieliński. I'm the manager of Research and Technology Transfer Department for the ML System SA. And the next speakers sharing the insights on the PV modules reliability and metrology for this session are going to be Marcello Passaro and Antti Tolvanen. Starting with Marcello Passaro, he's a member of Kiva Cermet Italia. Kiva is the leading independent testing, inspection and certification body in solar. In parallel, Kiva provides technical due diligence for PV parks and reliably scored cuts via PVL, a member of Kiva Group. Himself, Marcello, is their solar and storage expert. Marcello is also a solar enthusiast with experience in both upstream and downstream solar markets. He's been exposed to solar challenges in Southeast Asia, South America, China, Australia, India, and the Netherlands. He's particularly keen in informing others on the influence of the quality of design materials and installation on the lifetime of measured in kilowatt hours in production and revenue of a PV park. He does so from his experience in operating at this moment plus 200 megawatt of projects in Netherlands, consulting on the PV module procurement in LATAM, and upstream experience in testing the power and degradation of PV modules. All while coupling the collective knowledge of Kiva Group that have to date done more than 40 gigawatt of accelerated lifetime testing, batch testing, and technical due diligence. Today, Marcello is going to be giving presentation entitled PV Module Failures, Their Costs, and the Role of Certification and Testing in Mitigating those losses. Marcello, are you with us?
Yeah, I am. Thank you for the wonderful introduction. Honored to be here. A complete delight.
Perfect. Then the floor is yours, Marcello.
Yeah. All right. I don't know how. This is the first time I'm doing through Zoom. Can I see the slides, or do I have to share my slides? Can you hear me?
Yes, we can.
Okay. I have to. The slides will come automatically because I cannot see the slides.
We don't see them yet. Might be coming up just now. Let's give it a second.
Well, it's been great to see the conference so far. Seeing so many different innovations on Perovskites, solar. Even though I don't speak Polish, I can at least read some of the measurements, and it looks very exciting. So great work on everybody. Those innovations were needed to combat the climate emergency we're facing. So very exciting.
Thanks so much.
Yeah.
So I think the slides.
I cannot see the slides on my side, but I'll be happy to share my screen if need be.
Perfect. Then if you could try sharing your screen then.
Okay. Just in case, I think everybody should be able to see my screen now.
Yeah, it's up.
Wonderful.
Just make it full screen, please.
Okay, so today I'll be sharing a little bit more on the utility side. of PV. We heard from Bartoli from Impact earlier that profits are reducing in Poland, which was interesting to hear, and that there's an interest in movement, potentially moving towards storage. Yeah, and also from Monica from Becquerel mentioning about the risks associated with solar, and today I'll be looking a little bit into that, in particular module risks and how to mitigate them. So I'm going to jump right into the meat of it. So I'm going to tell you what I'm going to tell you, and then later I will tell you again what I told you. The idea is there are costs when regards to solar PV. So that's why you have the operation of the OPEX costs, but there's ways to mitigate high costs. And Kiwa can be your partner in progress to safeguard these PV revenues. So we're looking at modules. Modules, all in all, are up to 5% of all field failure events. Considering that they're 55% of the balance of system costs, this heavily impacts the revenues. What we have seen from PVEL, who is a Kiwa group member, from their latest reliability scorecard, is that there's a recurrence of typical failure mods occurring, particularly with new technologies coming out. So looking at half cuts, shingled, larger modules, and so forth. And that is the main root cause, but also because of COVID/Corona, there have been supplier changes, so changes in suppliers with regard to EVA, of encapsulants, glass, backsheets because of issues. We've also seen a spike in aluminium costs and so forth. So the main concern is that these can be, most of these failures in field at least can be mitigated through smart procurement and due diligence. But sadly, we are seeing a rise in that. So according to Solar Bankability, which also was funded by Horizon 2020 for a project of 10 cents per kilowatt hour, the costs are typically 5.4 euros per kilowatt peak per year. I'll be going later on what kind of mitigation steps you can do, but one of the first ones you can do, of course, is to make sure that the module has the right certificates. So the 61215 for quality, 61730 for safety. Then the following step can be the product qualification program from PVEL, where the tests are going through an accelerated lifetime testing with a specific bill of materials. And then a third one, and there are other steps, of course, is the contract optimization. So mentioning that it has to meet certain quality standards. So all in all, you can save up to, your costs go from 5.4 to 2.2. So all in all, you save 3.2 euros per kilowatt peak per year. This again is all to be reread in the Solar Bankability technical assessment of PV risks. Highly recommend reading that. I'll jump into the solar challenges and opportunities, and then go into the more common part of who we are, just to get the ball rolling. We would like to focus your attention on the kilowatt hour analytics, a paper which recently came out, where they analyzed about 800 parks in the United States, in which they saw that 20% of the solar PV assets, so those projects, were underperforming. What I mean by that is that the underperformance was that they were performing worse than their worst yield, so their P90 yield. There were various reasons to this. One of those reasons were failure events, irradiance bias, underestimated operational costs, or operational costs were 23% higher than estimated, and poor designing. So this can be due to workmanship and so forth. But what does this mean on a financial level? Well, on a financial level is that if you are, at least if you have such a high likability, as you see here, 96% probability, that you are going to do worse than your P90, there is a very high likelihood in that 7-year period that you're going to default on your loan. Just to give us a split, so most solar projects are project financed. So typically you get 70% from a loan or a loan from the bank, and you put 30% equity. Here in the Netherlands, it's 90% from the bank and 10% from your own pockets. So if you're not being able to pay your loan, this is a very big risk, especially when it comes to all these technical reasons. So we'll look a little into what are examples of typical failure events. As I mentioned, the frequency of an event of modules is quite low. It's only 5, worst case 10%, but the severity is very high because it's very complex to understand what's going on. So it can be light-induced degradation, light elevated temperature-induced degradation, potential-induced degradation, delamination, and so forth and so on. Another issue is that we see a lot of shading issues. There can be inter-row shading, shading due to objects. Initially, shouldn't really be a problem, but if it is a continuous problem, it can cause hotspots. It can cause diodes to occur, and moreover, if hotspots are present, this accelerates the degradation, which I'll be showing later. The actual real weak link in the chain are inverters. So the frequency of an event is very high, it's 70%. And this can be because of derating, they get too hot. So solar parks, just like people, if it gets really hot, often they work less efficient. Same thing with solar parks. But a lot of the reasons that the inverter fails is because of insulation faults. So let's say somebody cut a wire, some water gets in, there's an insulation fault, or a mouse has eaten a wire, there's an insulation fault, so the inverter will automatically shut off. So a large proportion of the inverter failures are actually are due to DC cable failures. But I'll be focusing more on the modules, given there's a larger interest because of the higher capex costs. So if we look at modules, we have to understand that a module is made of multiple layers. I mean, I don't have to explain that here. I'll be singing to the choir. But the frame is there for mechanical strength, glass for weathering protection. You have the encapsulant, which can be EVA or POE. That provides electrical isolation, but can also lead, if it's a poor EVA or poor POE, can lead to acetic acid formation, yellowing, which would also degrade the module's performance. Then we looked at the heart of the module, as Ali said from Jusong, is the cell. You have different cell architectures. You can use PERC, aluminum back surface field, TOPCon, PERT, so forth. They also have their own challenges, be it PID shunting or LID or LETID. Highly recommend looking at different papers from University of New South Wales on LID and so forth. And then the backsheets, multiple different kind of backsheets of suppliers. They're optimized for a longer life, but some are better than others, or some are made differently than others. And all these little variations in production can also impact the performance and reliability of the module. The next level is that we have to understand a module goes through a production line. So the cells come in, encapsulating glass, they all come together to make one. Each station can have small little variations, which you can have a big impact on the end product. One of the most critical parts of a production line is the lamination process. The lamination process is usually a good indicator of how the module will exist in the first 5 to 10 years, and the materials from the 10th onward. And a lot of the root causes we see are due to poor lamination, to usually delamination and so forth. And what we also need to see now from the research, the work that we are doing in pre-line inspection, factory audits, is that there is an uptake of new technologies. So shingled, half cuts, that means there's a very high learning curve on how to work with them. I mean, high learning curve is that more risk of having variations in the module quality. So that is why it's important to look at how is that workshop familiar with a new technology. So to put it into a bigger context, a Jinko, a Longi, a JA, a Trina, they have multiple location sites. So let's say one in Shanghai, one in Suzhou, Xi'an, Shangrao, and in that location site, they have multiple workshops. In those workshops, they have different production lines, different equipment, different quality procedures. So one workshop can do fantastic, great quality modules, and the other one can do less so it impacts the overall quality of that location. That is something that's often not taken into account, and there's also the seasonality of module procurements. When I was there, we often talked about around Chinese New Year, you don't want to buy modules because there's a big leaving of workforce during that period. Then there's a certification. The certification is absolutely critical to give an overall indicator of quality, but it is not a guarantee of quality. Why? Because the production module sometimes may vary from the certification module. So the certification module is based on a certain bill of materials. But as I mentioned before, the production module can change because of supplier issues. Then they have to change the material. But normally, a certificate is given for a set bill of materials. So we have the IEC 61215, which is for quality. You have the IEC 61730, which is for safety. The 61853, which is an energy matrix, which is for that PAN file that is used in the PV sys to determine what is the energy yield going to be of the project. And then you have different IEC 61215 for our PID, and as Monica mentioned from Becquerel, there are many different applications, desert conditions, hot and humid or tropical conditions. And for desert, you have different norms for hot temperatures and sand abrasion. And then we go into the accelerated lifetime testing. And I'll mention why that is important, because IEC 61215 should suffice. There is the accelerated lifetime testing because of the different applications. And then there's the PVL evolution product qualification program, which is 90% overlap with the brand new norm, the 63209, but it adds additional steps. And we often refer to by banks in the United States to be a critical part in the module procurements. You have to have a reliability scorecard. So why is the certificate sometimes not sufficient? Well, Fraunhofer or ISA had a very good point. They made the bathtub risk model. So in the first few years, you'll see more failures, and then it evens out, and then it goes up. But IEC 61215 should give you a good indicator of the first 20 years. However, because of the different applications, accelerated lifetime testing is needed. And you see this from the field, that despite the certificates, there are more failures than expected because of different applications. So what are exactly these failure modes and degradations that we're talking about? Well, this is very well studied. So in the first few years, you'll have light-induced degradation. This can then often what you'll see is junction box failures, glass breakages, or loose frames. Then light elevated temperature induced degradation can take years to degrade, but it will also recover over years. Midlife, you see PID issues. At end of life, you really start seeing delamination and EVA discoloration. So what is, as I mentioned before, about hotspots? The hotspots are an issue and about the different applications. So the overall median degradation globally is about 1% per year. But you see in different climates that they degrade at different levels, or there's more outliers, better said. So in hot and humid conditions, there's a lot more outliers or higher degradation. And if you put a hotspot next to it, so you see the blue is without a hotspot, red is with a hotspot, you have even higher degradation. The temperate conditions are more Northern European, and hot and dry, you can consider Mediterranean areas. So. But as I mentioned before, every production line creates different quality, and sometimes in that production line, one shift does better than another. Well, you see here that in one batch, the degradation is quite low, but in the next batch, the degradation is quite high because of the variance in cells and materials. And what we've seen to date, because we do a lot of batch testing of modules with regard to power, is that 40% of the modules that we test are below the minimum power level, which I'm going to be very interested what Antti Tolvanen will have to say, considering they have solar simulators and testing. So I'm very excited to see his results. As I mentioned, if you look at frequency, so I mentioned 5% of modules it's usually all pilot events are usually with 5% of modules. And then MREL looked at what is the frequency of a certain failure mod and what is the severity thereof. And as you can see, one really sticks out is hotspots. Hotspots are becoming are a very frequent issue and a very severe issue. LETD is an issue, PID and LID And there are different other topics which have to a lesser extent, but if you have under, for example, under nameplate value, you might get issues with your performance ratio, O&M is unhappy, EPC is unhappy, less yield, so this is a bit of a challenge. So what can you do to mitigate this? Well, there are multiple things that you can do. You can put in many different mitigation measures, but the solar market, because of the LCE, is very capex focused. So, and a lot of these quality processes are usually related to capex, and it also depends on the volume of your project. So if you have a 0.1 megawatt project, you're not going to throw everything at it. But if you have a 100 megawatt project, you have more money readily available for testing. So we looked at how big is a project, how much budget do you have for testing, and certificates are ready available. Typically, a tier one bankable module manufacturer should be able to give you the certificate with the bill of materials, provide a module of that bill of materials. The PVL provides for EPCs, IPPs, developers, and investors free data under NDA of the insights of all the reliability testing that's done. So that is cheap, it's free. You don't have to spend any money. Then the next level, you can look at contract optimization. So you spend legal money saying, okay, I want a gel content of 75% or better, a peel of X nanometer per centimeter, newton per centimeter better, and so forth. So each level, you can add more things. And batch testing, you can say, I want, according to IS 2859, so many samples tested with this kind of confidence, and then I have a bit of an idea. Factory audits to make sure the production line is making modules of proper quality. You can say, okay, I want to have even more trust. I want production modules. So while the module is being made, I want the lamination, so the temperature, pressure, and time profile of the lamination process is well concerned. Materials are properly adjusted. They're not using outdated materials. And then as last, you can do site testing. So EIV testing on site, EL testing, thermal, and so forth. But even that has different levels. So in all in all, adding all this, you lower the risk, you add maybe a little bit more CapEx cost, but you overall will increase your profits because you are having less costs in general. So falling back into what I said, as I mentioned, I will say what I said and I will repeat what I said. Modules are up to 5%. There are different technologies coming out. There are ways to mitigate it. Kiwa will be launching a module procurement guide in the next few months, which will show step by step how a procurement team or developer can watch out what kind of issues are there in the field, so that they can save the 3.2 euro per kilowatt peak per year. And then who is Kiwa? So I've been talking a lot. I haven't really introduced Kiwa. Well, Kiwa is a leading testing inspection body. We are in many different kind of sectors, but today I'll be focused on renewables. Renewables, particularly, we provide services in wind, solar, battery storage, and hydrogen. Hydrogen, we're very uniquely positioned because we're one of the few of the lab in Europe for testing hydrogen. And we do a wide range of services via TIC, feasibility, and so forth, and due diligence, very importantly. So for manufacturers, so for example, Impact unfortunately is not a customer of ours, but Impact for battery storage, we could do certification of their modules, of their batteries, but we also do certification of modules and inverters. We have a product quality program from PVL. We're leading in the European sector. For EPCs, we can do factory audits, pre-shipment inspections, accelerate lifetime testing. So we've done more than 30 gigawatts of upstream businesses of services to date. And for the investors and developers, to avoid, as I mentioned before, irradiance bias issues, the designing issues, we have the due diligence from Kiwa Moroni, where we can do owners engineering, technical advisory, and even do test reports on the batch testing. So just to give it a bit of a bird's eye view of what we do. So USA, we have PVL, who's a member of the Kiva group for the qualification testing of modules, batteries, and inverters. In the Netherlands, we have for pitched roof testing. In Germany, for battery and inverter certification. In Turkey, we could do the CTI values, for example, backsheet or so forth. In China, we can do lab testing, and in Italy, where we're mainly positioned, we can do a lot of the batch testing, certification of modules, also for larger inverters, because now we're going to inverters of 315 kVA, if I recall correctly. And you have, of course, the independent engineering, which we've already done international, and as you see, in so many different countries. So that's a bit of a presentation. I wanted to keep it short, given there was a little bit of an overrun on the other one. So I hope I didn't go too quickly. But if there's any questions, feel free to send an email. And yeah, don't forget to subscribe to our bi-monthly newsletter, where we send out white papers on different failures, what the costs are. So going in depth into what I just mentioned. So thank you all for your time.
Thank you.
Thank you, Marcel. Very interesting talk. At this point, I'd like to point out that brag a little bit that ML System is a holder of Kilowatt certificates for the PV modules, both in PV and BIPV. And we do recommend those guys. They are great. I think we have time for one question. If anybody dares, no questions. I'll have one then, Marcello. Do you think in all those failure modes, there's a way to differentiate between the BIPV, so glass-to-glass modules, and the standard PV modules, glass-to-Tedlar modules? Given that the BIPV is mainly unframed and PV is mainly framed modules.
I couldn't really hear the question, but from what I understood is what are the expected failure modes between glass-glass and glass polymer backsheet? Okay.
Yeah.
Well, I'm honestly not really an expert in BIPV, so I don't want to venture in that. I'll leave that to persons as yourself. But what we do see from the utility scale glass-glass modules, there are also failure modes. So we can, for example, if you use EVA instead of POE, you can see acidic acid formation, bubbling. So it's very important, the lamination process and what kind of EVA you're using in that. But you see chipping of frames that usually during production and installation. So every technology has its challenge. Glass definitely adds a level of security when it comes to micro cracks. You can walk all over the glass module, and it's very unlikely that you're going to make a micro crack. You do that with a glass polymer. Well, it won't look so nice in an EL. Don't recommend installing it. But yes, glass is a new technology. There are going to be reliability issues, and that will come up in the markets. We have seen, for example, PID was not known until it came out. LID wasn't known until it became a field issue. So, but all these accelerated lifetime testings that is being done according to IEC 63209 or be it PVL, you definitely will start to see, we can give an insight into what kind of issues may come.
Thank you so much. And again, so sorry to have kept you waiting. We have fallen a little bit behind schedule, but thank you so much for bearing with us.
More than happy. It was interesting to hear everybody's conversation. So I'm happy to listen to other people. I hear myself talk enough.
Perfect. Thank you. That brings us to our last speaker of today. Antti Tolvanen from Endas, Finland. He was born in the famous winter sports town of Lahti in Finland. He has studied in Helsinki University of Technology when he got his master's degree in characterization methods for dye-sensitized solar cells. He currently works at Endas from 2004 till today, now as Director of Operations. Antti, can you hear us?
Yes, I can hear you.
Perfect. Then the floor is yours.
Okay, thank you for the kind introduction. I'll jump right into it so we can finish for today. Can you see my slide?
Yes, we can.
Good. So the last talk will talk about latest testing activities in PV module manufacturing. A few words about our company and us. We specialize in solar simulators and other back-end PV module inspection tools. We were founded already in 2001 and are based in Finland. Over the years, we have delivered more than 600 systems worldwide. And our unique feature are the so-called all-in-one testing systems, which include all the back-end testing tools in one machine. This way we can save a lot of floor space and increase productivity. Here on the right, we can see the Quicksun 650, which is intended for production lines, and the Quicksun 650 Lab for laboratories. Both are these all-in-one systems. We have fairly strong presence in Poland with more than 14 systems delivered. My agenda is to talk about the trends in manufacturing metrology, mostly focusing on testing of PV modules in the back end, and we'll also look at some updates to standards in the IEC 60904 series. Well, as solar energy is starting to get a larger role in the energy sector, the quality of PV modules will have an ever-increasing role. Marcello already showed you very nice slides on this. I have here the graph from the latest ITRPV report on the left, which shows you that predicts that increasing warranty durations and reduction in output degradation of modules is an ongoing trend. And to support PV module manufacturers in their aim for better quality, IEC has released new standards on the subject. IEC 62941, Quality System for PV Module Manufacturing, supplements ISO 9001, and among other things, it gives best practices for module design, manufacturing processes, and for control of bill of materials. Another new document from last year is the IEC Technical Report 60904-14, Guidelines for Production Line IV Measurements. Standards can sometimes be a little dry on the content, but this technical report is very helpful in practical issues related to IV measurements. Estimation of uncertainty of module power measurements is emphasized in all new revisions of PV standards, and the factors affecting uncertainty are discussed in this technical report. There is background information on the effects of spectrum, irradiance non-uniformity, angular response of irradiance, module temperature, contact resistance, measurement cabling, and the proper use of reference modules. I highly recommend it to all PV module manufacturers. Another way of achieving high quality is to inspect the modules comprehensively in the factory. This is also a future trend according to the same ITRPV report as seen on the graph on the right. Output power and EL imaging, of course, are tested on 100% of modules today, but also other inspection methods are becoming more common across the production line. Automatic optical inspection, for example, shown here in dark blue, is not widely used today, but is expected to gain popularity in the future. I'll show more details on it later on. The use of MES enables statistical evaluation of manufacturing quality by combining process information across the whole factory. So my emphasis today is on the back-end testing of PV modules. Marcello also already showed you that lamination is a major source of faults. So finding faulty modules already at the factory is very important. After lamination, we have module trimming, framing, junction box curing, and this is then followed by module testing, which consists of module output power measurement in solar simulator, then electroluminescence inspection, shows micro cracks, soldering issues, and so on, that may not necessarily cause noticeable power loss in the solar simulator, but only in field conditions. Usually EL imaging is also performed before lamination here. But the final backend image is very useful because it records the state of the final product. Optical inspection can see some of the same faults as EL, such as displaced ribbons, cracked cells, but as EL imaging can only inspect cells as they emit light, optical inspection can detect other parts of the module, such as the frame, barcode label, and contaminations. Electrical safety test measures the insulation of the cells from the frame, and issues may arise if layout of cell strings is too close to the frame, or there is conductive contamination near the frame. Electrical safety test only identifies if there is an issue, but optical inspection can often see where and what causes the problem. A faulty bypass diode can lead to overheating of the junction box and to module failure. Let's then look at some of these tests in more detail and what current trends influence their features. First, solar simulator or flasher. Recent increases in cell sizes to M10, M12 are leading to larger increases in typical module sizes, of course. The handling of large, heavier modules increases need for automation, and this, of course, applies across the production line. Checking of the irradiance non-uniformity of solar simulator is emphasized in several standards, as effects of non-uniformity cannot be corrected in an IV curve. So large modules need large testing areas in simulators, so their uniformity measurement requires a lot of test points. So therefore, good tools for the uniformity measurement are essential. For example, we have integrated fully automatic uniformity measurement instrumentation in our all-in-one testing systems. Now, another point is the capacitance of modules. It's related to the open circuit voltage of the cells. Higher capacitance generally requires a slower measurement. There are several ways to measure highly capacitive modules accurately. Again, example, we use a calculation based on the physical model of the cell to eliminate the capacitive effects from the IV curve. At the bottom of the slide here is shown an IV curve of a heterojunction PV module measured with only a 50 millisecond long flash pulse. The IV curve has been accurately obtained using our capacitance compensation method. Then, bifacial modules generate electricity on both sides of the module. The recent IEC technical specification 60904-1-2 on bifacial IV measurements recommends testing bifacial modules on production lines on a single side only. This is accomplished by thoroughly characterized matching reference module that is used to calibrate the solar simulator. Then when the production modules are tested on front side only, their rear side performance is calculated based on the front side results and the reference module characteristics. Future challenges for solar simulators come with perovskite cells, as they exhibit very strong hysteresis in measurements. And depending on their composition, they may require different methods for accurate results. Perovskite output can also depend both on the duration of the test as well as testing history, which makes things interesting. Research into the subject is ongoing, and there are several good papers exploring these issues, such as the consensus statement by the leading researchers in Nature Energy last year. As already mentioned, EL imaging is a standard feature on production lines. Often, however, EL images are evaluated by operators, which can lead to inconsistency in acceptance criteria. But there's been recent improvements in image analysis with deep learning, so that now fully automatic software-based defect analysis and module classification is possible. Once this defect data is in the MES, statistical analysis of faults can help improve manufacturing processes. Some ways to analyze the data are, for example, defect type distribution, location and frequency of faulty cells within a module, shown here. Of course, this can be done based on each fault separately, or a heat map of overlaying cracks shows where the crack might originate from. All these can better identify the root cause of faults and then lead to better process control. In optical inspection, the module is illuminated with external light. Then a photograph of the module is taken and the software-based analysis shows abnormalities. The inspection measures distances of elements in the module. For example, distances between cells, between cell and frame, location of barcode or frame bending can be measured. It can see if ribbons are misaligned or bent due to insufficient soldering. Chip cells can be identified, loose cell pieces or other contaminations can be located. Lamination faults such as bubbling can be detected. And some examples can be seen below here. Modern modules have more than 100 cells and close to 10 ribbons per cell. So operator-based visual inspection is very time-consuming. So if we look at the module image here at the top, finding the bent ribbons is straightforward for the software, but not so for the operator. Well, here you can see a couple of bent ribbons here and a few here on the top. Faults here do not necessarily affect energy generation. For example, a missing 1 square millimeter piece of cell does not really lower module power, but correcting smallest faults leads to overall improvement in manufacturing consistency. Electrical safety tests are not mandatory according to IEC 61730, but for US market, the tests are required. On the other hand, adhering to the quality system for PV manufacturing requires that all modules be tested to validate their safety. Bypass diodes can be checked also prior to assembly to the module, but insufficiently organized ESD protection on the production line can lead to their breakage. So final testing of the diodes can also be warranted. Let's then look at the two main standards covering IV measurements of modules that have been updated last year. The first standard covers the classification scheme for solar simulators. The classification is based on 3 main characteristics of the solar simulator: spectrum, irradiance non-uniformity, and irradiance stability. The third edition's biggest changes have been made to spectrum classification. The wavelength range of interest has been extended, now 300 to 1200 nanometers, to better match the responsivity of today's modules. But existing solar simulators can still be classified with the old wavelength range of 400 to 1100. 2 new informative parameters were introduced: spectral deviation and spectral coverage. Informative means that they do not affect similar classification yet. The general spectral match classification looks at the spectrum at 6 wide spectral bands. Spectral deviation, on the other hand, is a measure how much, on average, the simulator spectrum differs from the reference solar spectrum AM 1.5G. The 2 pictures on the right show simulator spectra using LEDs and xenon. Both have a classification of A+. The green and red colors indicate spectral deviation from the reference curve, blue curve here. The spectral deviation for LEDs is calculated to be 4%, when xenon can achieve deviation of 35%. Lower, of course, being better. Spectral coverage identifies parts of the simulator spectrum where spectral output is low or none. These are indicated in the two pictures on the right with yellow. LEDs here have a coverage of 85%, when xenon can achieve a full coverage of 100%. The coverage is important when considering changes or variation in bill of materials, especially with materials that react to the far ends of the spectrum. If the UV transparent encapsulant has UV transmission issues and the simulator is lacking in coverage, this material defect will go unnoticed. So even though higher class of solar simulator indicates better equipment, the use of higher class simulator does not necessarily lead to lower measurement uncertainty. For example, effects of spectral match can be all but eliminated with the use of a matching reference module. Therefore, measurement uncertainty should be separately evaluated even when using a AAA+ class solar simulator. The second recently updated standard is the IEC 60904-1, which specifies procedures for IV measurement. The new edition has a lot of practical instructions on how measurements are to be performed. Emphasis is now given to the periodical check of solar simulators. Irradiance non-uniformity can be a fairly easy check if proper tools are available, and measuring spectrum of the simulator requires a fast 2-channel spectrometer to cover the now extended wavelength range. The standard has guidance for selecting either ISC or PMP as the reference for irradiance calibration. The table on the right summarizes the selection. On simulators with high non-uniformity, calibration using PMP is preferred, as ISC is more sensitive to non-uniformity. Temperature, conducting, cell capacitance, they hardly affect ISC when PMP is sensitive to them. So if there are known issues with any of them, irradiance calibration using ISC is then preferred. All things being well in control, calibrating using PMP can lead to a lower overall measurement uncertainty. There's also a new annex in the standard on methods to measure modules where capacitance affects power. Increasing measurement duration is one way to achieve good results. However, long exposure to irradiance heats up the module. Thermal inertia of the module can limit temperature rise during long flashes. But if the same module needs to be measured more than once, temperature effects become problematic. Strong emphasis is again given to the evaluation of measurement uncertainty. Here, the technical report IEC 60904-14 can assist. Sources of uncertainty are, for example, the reference module's stated uncertainty by the accredited lab and the chosen calibration method. Manual loading of the module can introduce variation, and conducting resistance can drift due to the wear of connectors. Temperature non-uniformity of the module or temperature drift during flash increase uncertainty, and measurement corrections are always made to the standard testing conditions, but also these corrections can add to uncertainty. So, in summary, latest standards emphasize the estimation of measurement uncertainty. Solar simulators classification is a starting point to lower uncertainty, but better classification does not guarantee low measurement uncertainty. The new versions of PV standards give a lot of practical guidance to better measurements. And overall, the trend in manufacturing to keep good quality is to inspect modules thoroughly. And all-in-one testing systems incorporate all backend tests in a single machine. And I'll thank you for your attention, and also any questions can be sent to me to my email address, if not asked now.
Perfect, Antti. Thank you very much. The update of the recent changes in standards. Are there any questions from the audience? Then I'll think I'll have one. Well, we are the owner of one of the 14 NDAS systems installed in Poland. I was wondering if, given the importance of the spatial non-uniformity within the system, is there a way, or is there a predicted way to handle or to rate very large modules? For example, modules that are actually larger than the solar simulator setup itself, which may happen in production environment, especially in our company.
So the question is that if the module is larger than the simulator, how to assess uniformity effects?
Exactly.
Hard question. Well, I guess if the system makes consistently the same kind of flash pulse, and you have a clear part of the module that you measure with one flash, then I don't see uniformity making a big impact on the result.
We had in mind sort of a reference sample made exactly the same way, and then scaling the results up to the modules of the proper size. That was one way, but it imposed some uncertainties. Giving
I'll have to think about it, and maybe we can continue this later on.
Perfect. Thank you so much again, and thank you so much for bearing with us up until the very end, even though we have fallen a little bit behind the schedule. It is my privilege to say that you have been picked as the best speaker of the session. Since you have since you are joining us online, we'll be sending you a little gift and token of the gratitude and the distinguish via post. So look forward to it. And of course, you're welcome to Poland anytime. Hello?
I can hear very poorly, but...
Antti?
Yes?
Can you hear us?
Yes, now I can hear you. Sure.
Perfect. So there's a prize coming your way.
Okay.
Perfect. Then look forward to it, and thank you so much for joining us today.
Okay, it was my pleasure.
Bye.
Okay, bye-bye.
Bye-bye.
Okay, then I think that concludes the session for today. I think everybody has earned a hearty lunch. I don't know, maybe not lunch, supper. Thank you so much for coming. Thank you the organizers and the PE Institute for making it possible, for making this platform possible, and for letting us share the expertise in the fields of photovoltaics today. Thank you so much.